Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. Today let's continue our series on probability distributions by going over a problem that will help us understand the difference between discrete and continuous distributions. And I think this is a really important concept because these two types of distributions can be very similar, but there are a few subtle differences. So what do I mean by a discrete distribution? A probability distribution that has a finite number of values. So in this case we have 0, 1/4, 1/2, 3/4 and 1. So the probability distribution on the left here can take 5 values, 1, 2, 3, 4, 5, and we're assuming that each of these values has equal probability. So that would mean that the probability of x taking the value 0 is 1/5, the probability of x taking the value 1/4 is also 1/5, and so on. So this is a continuous distribution. This is a discrete distribution. On the other hand, we have a continuous distribution where x can take any value between 0 and 1. Right? So x could take any real number between 0 and 1 is a possible value of x, and therefore we don't talk about the probability of x taking a particular value, but instead we talk about the probability density, which we represent by f of x, the probability density function. And since the total probability has to equal 1, we choose a value, or the value of f of x has to be such that the area under the curve has to be 1, or in more formal terms, the integral has to be 1. So here we're considering a uniform distribution where, given that the area has to be 1, we know that the area of this square has to be 1, and so the value of f of x would also be 1 for all values of x. So initially, although the values of the y axis, or the value of the probability here and the value of the probability density are different, these distributions are very similar in that the discrete distribution is basically tells you what values x can take between 0 and 1 with equal probability, and the continuous distribution is the same thing. X can take a range of values between 0 and 1, all with equal probability density. And so the problem that we're going to attempt today is one where we try to find the distribution of y equals x squared, and hopefully this can help us understand some very interesting differences between discrete and continuous distributions. So let's consider the first case. We have a discrete distribution here, and this is the random variable x, and we want to find the distribution of the square of x. So we can start off by observing that when x takes the value 0, y, which is the square of x, would also take the value of 0. Yes. When x takes the value of 1/4, y is the square of x, would take the value of 1/16. So that's somewhere here. And when x is 1/2, so we keep doing the same thing. When x is 1/2, y will be 1/4, with the square of 1/2 is 1/4. When x is 3/4, y is 9/16, which is a little more than half. And when x is 1, y would also be 1. And it has to, given that every value of x had equal probability, we also know that every value of y will also have equal probability, right? So y can take 5 values, 5 possible values, all with equal probability, and so the probability will still be 1/5, for all. Let me use a different color here. So the probability of y taking different values is still going to be the same, right? And so if we were to join the dots, this would probably look like a straight line. And so, one might expect that, you had a straight line here. When you square the random variable, you get a straight line. Similarly, you had a straight line here, and so maybe when I square it, I'm still supposed to get a constant value of y. And that is a good guess, but let's actually do the math to figure that out, right? So using a similar logic as before, when x equals 0, y, which is the square of x, would also be 0, and when x is 1, y, which is the square of x, would be 1. And so y can take a range of values between 0 and 1. And so just based on the pattern that we see here, I'm tempted to say that it's still going to be a flat line, because we know that the area has to be 1, and it was the probability density was 1 everywhere. So maybe when we square it, it's still going to be the same, right? So this is our initial guess. But let's actually work through the problem to see if this is indeed the probability density. So let me choose a different color. So this is our initial guess, but let's actually do it the more formal way to find out the distribution of y. So we know that the integral of the distribution over the range of the values y can take, so over the range of 0 to 1, that has to equal the integral of the original probability distribution over the values that x could take initially. So that has to equal x ranging from 0 to 1, f of x dx. And maybe I should have specified this, but g of y is the probability density of the random variable y. So we're just using g of y and not f because it could be a different function for all we know, right? So now we have, and yes, y and x are connected by this equation that we had seen earlier. So we just adjust it. Perfect. Okay, now we have we know the relation between y and x, and we have an equation that connects y and x. So let's try to eliminate one variable so that we can find g of y. So y is x squared, dy would be 2x dx, and so just rearranging, dx would be dy over 2x. And because we're considering x to be from 0 to 1, y will also range from 0 to 1, and therefore x must be the square root of y. And this is not a problem because x is only positive here, so we can confidently say that y will be the positive square root, or excuse me, x would be the positive square root of y because x only takes positive values. So hope that's clear. Let me just create a little more space. So x is the square root of y, which means if I plug the value of x back here, we get dx equals dy divided by 2 times the square root of y. And let's plug this back in. Let's substitute the value of dx here in this integral and this value of x over here. So rewriting this equation, integral y varying from 0 to 1 of g of y dy equals f, x is the square root of y, dx is dy over 2 times the square root of y. And now because we have changed the variable from x to y, the limits of the integral will also change. But fortunately, when x ranges from 0 to 1, y also ranges from 0 to 1 because y is the square of x. Great. And now we have two sides of an integral, or two sides of an equation with an integral which have the same limits and the same variables, and so we can very easily equate the thing that we're integrating. So g of y must be f of square root of y divided by 2 times the square root of y. And what is f of square root of y? Remember, f of x was 1 everywhere, right? Let me just write that down. F of x was equal to 1 for x in the range of 0 to 1. And so, and because y is the square of x, y would also range from 0 to 1. And so the square root of y would also range from 0 to 1. And so f of that would still be 1, right? Hope that makes sense. Because f of, whatever you input to the function, as long as it's between 0 and 1, it's going to output a 1. So by the same logic, square root of y is going to lie between 0 and 1. And so when you input that to the function f, it's going to output 1. Right? And we are almost done. So g of y is 1 by 2 times the square root of y. And of course, this is for y ranging between 0, and I should be careful here because 0 cannot be a part of the domain. And yes, so this my friends is the distribution of g of y. Isn't this interesting? If we were to try to graph this, it's 1/2 divided by the square root of y. So when y is 0, this is going to tend to infinity. And when y is 1, it's going to take the value. Let me actually make sure the graph is drawn to scale. So when y is 0, this would tend to infinity, and when y equals 1, this is going to be 1/2. And this is the function, and this is g of y. Isn't this interesting? When we had very similar discrete and continuous distributions where x could take a set of values between 0 and 1 with uniform likelihood, and all of a sudden when we square it, the discrete distribution doesn't really change, whereas the continuous distribution takes weird 1 by 2 times the square root of y form. So I encourage you to pause the video here and try to reason as to why this is happening. Okay, assuming you have paused and tried giving it a thought, the way I like to think about it is that x takes values between 0 and 1, right? So when you square it, when you're squaring a number that lies between 0 and 1, it is going to get smaller, right? And so as let's say your value of x takes let's say it takes 1/4 or 1/8 initially. When you square it, you're going to end up with a smaller number that lies close to 0, and therefore all of the numbers that are close to 0 when squared are going to get even closer to 0, which is why you get very, very high probability density around 0. And as you go towards 1, if you think about it, the only way you can reach a probability density, or excuse me, the only way you can get to y equals 1 is when x equals 1, right? Because if you squared any number that's less than 1, it's going to get smaller. So you have to get really, really, really close to 1 for the square of it to be 1. So that is why we notice this decreasing trend where the probability density of y is low around y equals 1, and it gets very, very high as y equals 0. And so I hope, when I first learned about this, I found it very interesting to know that even though two distributions were very similar, when you square it, the random variable, the distribution can change. So I hope this was a very useful insight for all of you, and I will see you in the next video. Take care. Bye-bye.